In this video, we're going to talk about the definition of the derivative at a point. And so we've already seen sort of half of the definition here, but we're just going to introduce some new terminology, namely the derivative of a function at a number and the notation for that. So the derivative of a function f of x at a number a, and that's denoted by f prime of a, that little sort of dash or apostrophe up there. So that lets you know that this function is related to some function f, but it's not exactly the same. That's the prime lets you know that it's something related to the function f. So f prime of a is defined by the derivative of f at a is the limit as h goes to 0 of f of a plus h minus f of a over h. So if you recall, over here on the right hand side, this was the solution to the tangent line problem. This expression will give you the slope of the tangent line at some point on the graph of the function f. So that part's not new. We're just now going to call that the derivative of f at some number a, and we're going to use this notation here, f prime of a. And of course, all of that's if the limit exists. So remember, if the limit exists, if the limit exists, then f is said to be differentiable at a. So this is a property of a function at some number a, just like similar to continuity, right? We said f is continuous at a if f satisfies the three properties for continuity. So now we're going to say that f is differentiable at a if this limit exists. Okay. And what f prime of a is, of course, is the slope of the tangent line to the graph of y equals f of x at the point a comma f of a. So from last time, recall, right, that's the solution to the tangent line problem. Okay, so the derivative gives the slope of the tangent line. All right, let's take a look at a couple of examples. Example number 1, if f of x is x squared minus 3, find f prime of 2. Okay, so there's the definition of the derivative, f prime of a, right? And here a is going to be equal to 2. So we replace a by 2. Okay, and so now the very first thing that you're going to want to do on the definition is to evaluate this top part right here. So this is f of 2 plus h. So what that is saying is take this stuff inside parentheses and plug it in for x in this function right here. So generally, for most people, that's the most difficult part to get a handle on. Okay, and then over here, I'm going to plug 2 in for x also. Okay, all right. So when I do that, I get 2 plus h squared minus 3. So again, a lot of people get confused. Where did this come from? Well, look, all I did was right here, here's f of x, and then I plugged in 2 plus h. So I'll have 2 plus h squared minus 3. So all this stuff right here is f of 2 plus h. And then the minus came from here. And then f of 2, well, that's what I get when I plug in 2. So I get 2 squared minus 3. All right, so the next steps involve just simplifying this top part as much as you can. Of course, this needs to be FOILed out, right? 2 plus h times 2 plus h. And then 2 squared is 4. So foiling this out, I get 4 plus 2h plus 2h plus h squared minus 3 minus 1 all over h. So I've got a bunch of like terms up here. I want to combine all those like terms. So I have 4 minus 3 minus 1. That adds up to be 0. And then 2h plus another 2h gives me that 4h right there. If you try to plug in the 0 at any point here, you're going to get 0 over 0 no matter what. That's just how this definition is. So, but you can see here that every term on the top has an h, and there's an h down here. So what you want to do is to factor out that common factor on top, and then of course cancel it with this h on the bottom here. So now I have f prime of 2 is the limit as h goes to 0, 4 plus h. That's an easy limit to compute. And so I just wind up with f prime of 2 equals 4. Okay? So that's how you would compute that out, the derivative of f at 2, right, using the definition, and it comes out to be 4. So let's take a look at the graph of the function. Here is the function f of x equals x squared minus 3, graphed out. Okay? And here is 2, right? Our value for a was 2, and so the point on the graph corresponding to 2 would be 2 comma 1. And again, if only the x value is specified, you can get the y value by just plugging 2 in for x, and you're going to get 1. So there's the point here. Here's what the tangent line looks like, right? And remember, the derivative, which came out to be 4 in this case, is the slope of the tangent line. So if we take a look at the tangent line, right, the blue line right here, and just take any 2 points on it and look at the rise over run, right? So the run here would be 1, right? And the rise would be 1, 2, 3, 4. So rise is 4, run is 1, so rise over run is 4. So indeed, the tangent line has a slope of 4, just like we calculated out there. Okay? All right. Let's take a look at another example. All right, we're just going to look at the same function, but now instead of finding the derivative at 2, we're going to find it at 3. Okay, so again, same type of problem here. We use the same definition. We want to know what's the derivative at 3. So there's the definition. We replace a by 3, and we calculate that all out. Very similar to what we did before, right? Here I have f of 3 plus h, so I would plug 3 plus h in for x there and get 3 plus h squared minus 3, and then I would plug in 3 also up here, get 3 squared minus 3, and then do a lot of simplifying. But you notice it's almost exactly the same steps that we did before. The numbers are just slightly different in this case. Combine all the like terms, and that's what we're going to get. And then factor out the h, and then cancel, and then take the limit, now that we won't get 0 over 0, and it comes out to be that f prime of 3 equals 6. Okay, so if you notice, the steps between this problem and the previous example were very, very similar to each other. So what we're going to do in the next video is talk about a way where you don't have to repeat that work over and over again. You can just do this calculation once and get a formula for the slope of the tangent line, and then just plug in the numbers when you want to find the derivative at some number. So when we refer to that calculation, we'll just call it the derivative. So one more time, let's take a look at the graph of this example and just look at that. This time the point was 3, 6 up here, and there's our tangent line. We calculate that out, and again we're going to look at the rise over the run. The run in this case is positive 1 right here between this point and this point here, and it goes over 1, it goes up 1, 2, 3, 4, 5, 6. So the rise over run, the slope of that line is 6 over 1. So again, the graph here agrees with our calculation. Okay, so like I said, in the next video we are going to take a look at this example again and look at one new definition, and they are closely related to each other. In the next section, it's just a way to repeatedly calculate derivatives at numbers without having to work through all these calculations every single time.